Thank you very much, Corinne, for the introduction and the organizers for inviting me to this very wonderful environment here. I have to begin with an apology, and the word apology comes later on also in my talk in a different context. Apology for this kind of very ambitious and kind of pretentious title, but fortunately I can quick show what I really want to say, and that fortunately I can base my talk partly on several very interesting talks on applied mathematics already at this conference by Caroline, Tin, everybody here, so several ones also, the AI in modern text recognition and similar things. This is also, I have to say that this book inspired by two recent books by Prof and Gorielli, that are leading applied mathematicians in Oxford, Prof now back in the US. Basically what I really want to say in one sentence is to look at what applied mathematics means, who are the bearers of applied mathematics today, and what does it imply for our changed look at the past, because apparently, as I hold, there are things which have been neglected by looking at the past by which was so far nourished mainly by the perspective of pure mathematics, or at least that there are demands to add. So you see some of these things which I'm going to discuss partly. So I'll begin with Trefethen's short book. He, in his An Applied Mathematician's Apology, he refers, of course, to Hardy's A Mathematician's Apology of 1940, while the latter was an apologia of a pure mathematician vis-à-vis the public in wartime. Trefethen's is a defense of an applied mathematician vis-à-vis pure mathematicians in times of peace, if we have peace today. So my life is mathematics, and I feel a strong connection to the mathematicians of the past. My sense of myself as a mathematician just gets stronger, and yet I feel a disconnection from the mathematics and the mathematicians of the present. So you see there is a kind of contrast immediately being shown here. Then we have another booklet, which is in the series of mathematics and a short introduction, or the other fields, not just mathematics. This is this Belgian mathematician Gorielli, who is still in Oxford in his chair for modeling mostly, which came up before. So Gorielli divides applied mathematics by three intertwined areas: modeling, theory, and methods. People might miss now calculation, whatever. So there are several layers you can divide mathematics. And also, apparently, is also related much to academic applied mathematics. And he says, I'm one of those researchers who develop methods. Trefethen says, methods, rather models. The same goes for many numerical analysts, though not all. It is sometimes said that our focus is on applicable than applied mathematics. So this is also typical in a way for academic applied mathematics, as I would characterize it, while applications of mathematics, outside mathematics, lie some other place in a kind of classification. And he says, Trefethen, I consider myself qualified to have opinions about continuous mathematics, but not about discrete mathematics, pure or applied. Donald Knuth has been a career-long inspiration to me and also a friend, but he is at heart a discrete mathematician and the continuous side of algorithms got mostly left aside by him and his circle. Computer science is a study of algorithms for the problems of discrete mathematics. So one might wonder why now this continuous comes in, because algorithms have obviously also to do much with discrete, right? We have to consider this in a specific sense to, for instance, calculating numbers which are irrational by as far as possible. So this is another one which is certainly in need of interpretation, taken from Christopher Siemann, reproduced by Gorielli, and he takes up also this discrete continuous classification, but in different ways. It can be discrete, part of it can be discrete, continuous, and depending on the object and on the mathematical method. By behavior, he's apparently also alluding to the mathematical methods used in this context. But this needs more, maybe you have a short look and look it up also for yourself in Gorielli's book for further understanding. I cannot fully interpret it here. So who are the applied mathematicians, I'm asking? I see a contrast between academic mathematicians versus the ubiquity of applications in industry and in military. So Trefethen says, demographically we are big, accounting for perhaps 5% of academic mathematicians, and in impact on science and technology we are enormous. I mean, given this change to computing today, one is first surprised that it's only 5% in academic mathematicians, but he still then apparently points to the region outside of mathematics for the impact on science and technology. And of course, there are all kinds of applied mathematicians that need not have a degree in mathematics, but they can be engineers, physicists, or some. We cannot divide this. We have to consider the whole field. I do numerical experiments. Whatever the topic, I use the computer to guide me. This applies when I'm working on algorithms and also when I'm working on theoretical problems. So surprisingly, common error is to suppose that mathematics has proofs instead of experiments as a source of knowledge, when in fact it has proofs in addition to experiments. So I mean, so he's now speaking for the whole of mathematics, right? Because you have also experiments in pure mathematics. But it is only a recent kind of phenomenon, also the philosophy of mathematics. For instance, we look at this book by Hirsch and Davis, Mathematical Experience, that this informal side of mathematics, also pure mathematics, is being clearer outlined. And so in a way, this is also path-breaking for our look, this book, for our look at applied mathematics. So there's a widely held view that mathematics is one, so it's united. But the difference between pure and applied is illusory. This is nonsense now, Trefethen says, right? And in my experience, it's generally an opinion held by pure mathematicians who often fancy themselves applied, or fancy they could easily be applied if they chose, right? So this shows his problems also of his apologia. Gorielli goes, especially in chapter 7, in the direction of this known article, Unreasonable Effectiveness of Pure Mathematics in the Natural Sciences from 1959, this physicist Wigner. And while he quotes all these known examples of whatever, Diophantine algebra, of conics, and of number theory, who kind of found later on unexpected applications, right? So this is an unreasonable thing. But this, I mean, and then he adds new examples like quaternions and knot theory, which have shown recently unexpected applications. But this is kind of this mystery story, right? Where you're saying, well, we don't really know where it comes from, but we produce it in store, and at some point it will be applied, right? So this is not really what we as historians would like as analysis, just to be surprised all the time. So both have showed some affinity, both Trefethen and Gorielli show some affinity to history of mathematics. So Trefethen dedicates his book in memory of Karl Runge, a kindred spirit from another era. And Trefethen says, also, I joked occasionally that numerical analysis is a study of the mathematics of the previous century. So going back to existing pure mathematics and then adding its usefulness. And Gorielli says, I wish I could stand on the shoulders of 2,000 years of history and intellectual achievement and affirm with pride that I'm a mathematician in the tradition of the ancient Greeks. But he should say he stands actually also on Greek shoulders if you look at Archimedes and Ptolemy. Unfortunately, the situation is not so pristine when it comes to mathematics, as oxymoronic sibling, applied mathematics. So they feel a divide in the tradition. So what is the consequence for us as historians? Well, we have to trace the specific historical traditions of applied mathematics, and we could use them for bridging the apparently perceived divide between pure mathematics and applied mathematics today, and between the historiography of mathematics and the sciences, which were also mentioned by Karen Pasha in the talk today. I mean, this is not being recognized as a good history of science, history of mathematics. So June and June, by the way, helped me also for the preparation of this talk. We published in this Princeton Companion for Applied Mathematics by Hyam edited a chapter on the history of applied mathematics. It goes rather general terms, but we found some points maybe worth considering. So this is the beginning of the scientific revolution, and Bacon, Francis Bacon feels that this mixed mathematics, which was an old notion for applied mathematics, being used by Brits partly into the late 19th century. So this was an upcoming topic. It changed something when we have a periodization of applications in mathematics, and we stress certainly that applied mathematics was in a way, in many periods, the normal case, and the pure mathematics kind of came as a kind of when special needs also for pure mathematics came up. For instance, 1890 to 1945 in the second industrial revolution, and then of course with computers in an even stronger form. So we have to look for the societal needs which provoke at any historical period special attention to applications. So in Rio de Janeiro, I had a talk in this History Congress on what I call the historical triangle of methods in applied mathematics. I saw this kind of a triangle because we have graphical methods, numerical methods, and then at each time instruments. And of course, there are gliding transitions from graphical methods to instruments to apply these graphical methods, also to hardware for apply or implement numerical methods. And in a certain sense, the graphical methods have a kind of continuation in analog computers, while the numerical methods a certain continuation in digital computers. And in all, of course, always existence problems and accuracy play into this, and a kind of dialectics between graphical methods, which were partly later on transformed into numerical methods. But this is basically, I would think, because graphical methods lost much we can discuss this, but of course there are computer graphics today and stuff, but at the period of around 1900, they lost against numerical methods, and several of them were kind of translated into numerical methods. So this might be a thing which is no longer accurate to be used today with totally other conditions with computer science, for instance. So then, to get more to the point, what is the difference between pure and applied mathematics? Gorielli says, Richard Courant, who in 1935 founded one of the first centers of applied mathematics in the US, the future Courant Institute at New York University, once said, applied mathematics is not a definable scientific field, but a human attitude. The attitude of the applied scientist is directed towards finding clear-cut answers which can stand the test of empirical observations. So this puts, again, the question of the existing societal needs to instill these attitudes, right? This can, of course, be done by education. So this is crucial in this respect when the nation states came up and in connection with the great industrial revolution, that in a way educational systems had to firstly take care also both of pure and applied mathematics, but it didn't immediately need imply applications in industry. So the engineers had kind of again to install this mind by education to the engineers as a tool, certainly for Soleil and so on, but it didn't immediately apply, for instance, machine construction or something. So societal needs can, of course, also be philosophical and political in this sense. I mean, even Platonism or whatever can be defined as a societal need for the philosophy of the time. In a sense, one has to look at this broad, both applied and pure mathematics. And then we have the preference for pure mathematics among the Bourbaki generation, or with Hardy in this book, right, on the apology. And they referred frequently to Jacobi's well-known quote, proclamation of the honor of the human spirit. This stimulated me once to look at this quote once again and how it was stimulated. This quote by Jacobi. So it was an German article 2013. So Jacobi writes to Legendre, both were working in elliptical functions, elliptical integrals, as you know. And it is true that Monsieur Fourier had the opinion that the principal aim of mathematics was public utility and the explanation of natural phenomena. But a philosopher like him should have known that the sole aim of science is the honor of the human spirit. And under this title, a question of numbers is worth as much as a question of the system of the world. There's a certain contradiction in this quote itself, because he says, he emphasizes the question of the system of the world, which was, of course, in a way included in the explanation of the natural phenomena, right? So it's a little bit contradictory in itself. But now, while looking, what is he actually alluding to, Fourier here in this letter? And some utterance, some remark by Fourier. Then I looked first for the Théorie analytique de la chaleur from 1822, and one finds only the following: profound study of nature is the most fertile source of mathematical discovery. This is not to say that Fourier was a stranger to public administration or public benefit. Quite the opposite. He was quoted, I think, by one of the talks on statistics, which we had before. But it's not there in the book. And then I looked at this letter, closer at this letter, but there's another passage in it which alludes to a slight criticism of Abel's and Jacobi's work on elliptical functions by Fourier in an address to the French Academy of Sciences of 1828, when he says, "The theory with which they have concerned themselves is a vast subject requiring great effort. It is singularly suited to showing the immense fruitfulness of analysis. But the questions of natural philosophy, whose aim is the mathematical study of all great phenomena, are also worthy and the principal object of the meditations of mathematicians. It is to be hoped that those most capable of perfecting the science of calculation will direct their word towards these lofty applications, so necessary to the progress of human intelligence." So, see, again, he reduces it to natural philosophy, doesn't speak about public service or whatever. And so the use of this quote by Bourbaki is in a way kind of partisan and kind of inspired by their interests. And if one looks closer at Jacobi as a person, then one should not forget that he, in a sense, he can be, or he was used by Bourbaki as a kind of representative of the purest turn of German mathematics, which Bourbaki found very attractive at the time, because they were influenced by the algebra in Germany at the time, and axiomatics. That again, he cannot be actually considered a typical representative of pure German mathematics, because he was earlier in a way, and he was still in the tradition of Gauss and his broad view of applications. And if you look at Goldstein's, which I recommend as an important work for history of applied mathematics, in his history of numerical analysis, he says Jacobi interested himself in a number of aspects of numerical analysis and so on. And then he quotes this saying, über ein leichtes Verfahren, die in der Theorie der Sekundärstörungen vorkommenden Gleichungen numerisch aufzulösen, in Krennes Journal. So he was not a forerunner to applied mathematics either. So that's a kind of also historical falsification by Bourbaki when they consider him this way. So Trefethen again, half a century on, after 1945, has grown into one of the largest branches of mathematics, the specialty of thousands of researchers who publish in dozens of mathematical journals as well as application journals across the sciences and engineering. Thanks to the efforts of these people going back many decades, and thanks to ever more powerful computers, we have reached a point where most of the classical mathematical problems of the physical sciences can be solved numerically to high accuracy. So he says most of the algorithms that make this possible were invented since 1950. So you know, around the end of the war, these numerical digital computers came up, and this is total different mathematics which we have after the war, in a way, if we consider this background. And these algorithms, many of them have historical ancestors, and he's also alluding to them, as we saw in the Jacobi quote, but it is a total different mathematics, and we have to act accordingly. But still, he's apologetic, Trefethen. He wants to be taken seriously as a mathematician, right? He says, unfortunately, the habit in the numerical analysis literature, so in his literature, is to speak not of the convergence of these magnificently efficient methods, Adams and Rome-Kutta, but about their failure, about their error, or more precisely, their discretization of truncation error as distinct from rounding error. This ubiquitous language of error analysis is dismal in tone, but seems ineradicable. So then he goes into what he considers also to show the respectability of of numerical analysis, which is the focus of this talk anyway, of my talk. Then he refers to German Dahlquist and this kind of fundamental theorem of numerical analysis. Consistency plus stability guarantees convergence in a sense. I cannot, but of course, instability is kind of accumulating of local errors, and the things gets out of control. But he says experience indicated that as a practical matter, a method would succeed if it was not unstable. And then he's referring to very theoretical work on applied mathematics, this Lax equivalence theorem, published by Lax and Richtmeier in 1956, and says these things. The theory was restricted to linear equations, whereas Dahlquist theory for ordinary differential equations also apply to non-linear ones. But broadly speaking, the new result followed the same pattern of equating convergence to consistency plus stability. Mathematically, the key point was the uniform boundedness principle. Of course, that's a principle from functional analysis, so he really connects himself here to abstract modern analysis also, to show the respectability of his field and his so June and I, in our article, we felt it necessary to write that the importance of attitudes notwithstanding, by any definition, applied mathematics has to be genuine mathematics in the sense that it aims at or uses general statements. This came up in connection with Frederick's talk, right? The generality of mathematics, the function of thought economy. In fact, the applicability of mathematics is mainly based on its generality, which in relation to fields of application often appears as abstractness. This is even, I like this for my students, to the elementary applications such as the use of the place value system, right? Because that's basically proven through the centuries. It's proven without ever really attempted, but it needs a proof, right? That every natural number can be represented by it, and this the representation is unique. But it's a fundamental theorem. I still believe that applied mathematics has to be defined as parts of mathematics with its special traits, such as generality, in order to distinguish it from the various applications outside mathematics and from hybrid disciplines such as fluid dynamics. However, it seems to be necessary to stress that mathematics as a whole, and also the notion of proof and rigor, have changed dramatically, particularly after the entrance of electronic digital computing. Examples are the proof of the four-color theorem and the convergence of algorithms. I think Ursula has indicated the importance of these computer-assisted proofs. But of course, this can be related to different styles or attitudes of pure and applied mathematicians. Look at these quotes which are coming up. Oh, I think I get it. So this has been quoted quite often by Poincaré, Les méthodes nouvelles de la mécanique céleste, volume 2, chapter 8. And there he's talking, especially, of course, in a translation by Gorov, I think, various meanings of the term convergence. Between mathematicians and astronomers, some misunderstanding exists with respect to the meaning of the term convergence. Mathematicians who are mainly concerned with perfect rigorousness of the calculation and frequently are indifferent to enormous lengths of some calculation, which they consider useful, indifferent, so they don't care about, without actually thinking of ever performing it efficiently, stipulate that a series is convergent if the sum of the terms tends to a predetermined limit, even if the first terms decrease very slowly. Conversely, astronomers are in the habit of saying that a series converges whenever the first 20 terms, for example, decrease rapidly, even if the following terms might increase indefinitely. So you use this example, right? These astronomers used infinite series, either Fourier series or power series to approach the differential equations of astronomy. And this is the general term here of one of these series, and you see this term grows immensely in the first 1,000 terms, right? That's a general term of the series, which has to be summed up afterwards. While afterwards it decreases, and of course the thing can easily be shown to fulfill the necessary condition for convergence of series, namely the zero sequence, right, of the general term. While this one is clearly not convergent because the necessary condition is not fulfilled, right? But it's in the first terms it goes to zero, so that the sum goes slowly seems to go to a limit at the time. So he was fully aware, and then I use this occasion to refer to a recent historian of applied mathematics, Dominique Tournès, because he is exactly looking at these mathematical astronomers of the 19th century and saying we cannot get a picture of applied mathematics if you don't look at these kind of cultures which are not really included in mathematics. And so he has worked both on these methods for integration of differential equations, so these kind of algorithms or difference methods and stuff, and also on the calcul graphique, right, where he says jusque vers no, 1970, I could get it in French. The thing played a big role, right? But also indicating that the role is now just going down for the graphical methods, right? So he's one of the kind of leading historians of applied mathematics, I would think, today. And then a quote from Lax. There's Hirsch, who I mentioned before, with his philosophy book, right, with Davis, and he writes a book, Peter Lax, Mathematicians, and an illustrated memoir, which I've reviewed for the Intelligenza. And there he says first this one, this quote from Hirsch. He's an immigrant from Hungary to the US. It's a fundamental theorem which was mentioned before. And then Hirsch nevertheless points to Lax's conviction of the existence of different styles in pure and applied mathematics. He quotes Lax, "There's really a different point of view. Take three-dimensional or even two-dimension compressible flow calculations in R. I don't think we will ever be able to prove that the computed solution is within a prescribed epsilon of the true flow. That's hopeless. And if there were such a proof, it would be unenlightening." And then comes a point which I find very interesting. It's far more convincing that calculation carried out by an entirely different numerical method gives a very similar result. So they're comparing two algorithms, both of which they don't know whether they converge, really, in a strong mathematical sense. But because they give the same result, they are accepted. So this goes outside the kind of consideration which Jefferson had, right, for the respectiveness of applied mathematics. So yes, obviously problems with modern pure mathematicians, Jefferson. So he says, in some people, the idea apparently being a good scientist can figure out computational methods on the fly as needed. And he says he has never profited from Fields medalists mathematics for his applied research. Right? So he says still too abstract. Nowadays, most leading mathematicians have little interest in calculation, which they avoid by habit and may disdain as unimportant in principle. It is a mystery to me why more mathematicians don't recognize numerical computation as an indispensable way to explore mathematics. This is the year 2022. I mean, we have to take it somehow into account, right, if this guy says it. This does not sound, but this does not sound so different from what Richard von Mises said 1927, so almost 100 years ago, about his fellow pure mathematicians. He was an applied mathematician. Although the available technology for computing has changed totally since then. This gives us the opportunity for a digression into German traditions, which I worked mostly on in my publications. We have Courant, he was quoted before with the human attitudes, but at the time, in 1927, when this quote comes by Richard von Mises, he's kind of an object of his criticism. He criticizes him because what he does is, Courant, the successor to Runge in Göttingen was filled by Helmholtz, what's the name? A different pure mathematician, but certainly not one of the kind of Runge, right? And he said it was no longer necessary to divide these things between applied and pure mathematics. Mises was critical, at times contemptuous, of those pure mathematicians, as he wrote in Die Naturwissenschaften, belong to the overwhelming majority of our university professors who declare with more or less pride, at least however with full justification, that they are unable to perform the smallest numerical calculation or geometrical construction. So this is 100 years ago, and Trefessen seems to be of the same opinion today, at least for counting or for calculating. So we should not forget, of course, Felix Klein, the great reformer who had these talks at the Evanston Colloquium, the home of our colleague Sandy Sabel in the back. And so I could quote many things from this quote here, which I just take this one about refined intuition and naive intuition, and in this context. And Renate Tobis has recently published in 2021 this biography of Felix Klein, who is 100 years dead now this year, right? There's, by the way, also the quote, this notorious quote about the Teutonic and the Aryan spirit, or whatever, in mathematics, which has been misinterpreted and put Klein into the category of anti-Semitism or something. The same talk, but this is another topic. So we have Runge here to show his picture. He wrote, as you say, this kind of parallelism of graphical and numerical methods at the time. He was at Columbia University, gave as a guest scholar, and published on graphical methods for the Americans, which was at the time new for them, but with an appendix which is important on numerical methods, for instance, the Runge-Kutta methods. And then women come into it, not just as mere calculators, which they often have been, right, in the history of mathematics, but also with theoretical level and equality. The daughter of Karl Runge, this is wonderful German quote, which later disappears, unfortunately, in the English translation of the book. Tomorrow I want to calculate once again 100 wonderful things. So to show her enthusiasm, right? She was in industry, Osram and Telefunken. And then we have Richard von Mises himself. Klein, you knew him from the beginning. He cooperated in the encyclopedia with Klein of mathematical sciences, and he called von Mises, who apparently is one of the most successful crossbreeds between mathematics and engineering. So this was a time when the kind of institutional and cognitive barriers between mathematicians and engineers would crumble, and von Mises was the first director of the Institute for Applied Mathematics in Berlin and co-founder of the professional journal ZAM and the Society GAM. Co-founder is actually too little for the ZAM because he really was a spirit here. But for GAM he was co-founder. And as a Jew he had to to leave Germany in 1933. And this is the first issue of the journal Zeitschrift für angewandte Mathematik und Mechanik. And you can see, that's here the introduction, über die Aufgaben und Ziele der angewandten Mathematik. So the journal is for angewandte Mathematik und Mechanik, but he speaks here only about angewandte Mathematik, so that shows the emphasis on really angewandte Mathematik in the journal. But he really cooperated with engineers who published quite a few, not experimental, but theoretical engineering stuff. And in this, I've analyzed this thing and partly translated in an article also in Sun. And then this has the title, "The Joy That Engineers and Mathematicians Have Come Together." And who does a quote? The quote is from Klein in the dedication to the journal. So I quote it. So he was happy that towards the end of his life that one of his plans. And then it was fulfilled. And then we have this, coming back to David's talk, popularization of mathematics and entgiftete Mathematik, which means decontaminated mathematics, about the Institute for Applied Mathematics. It was in an illustrated journal, weekly or something, Koralle. And when we show a layperson at the Institute, we lead him to the electrical calculating machine first. It divides a 16-digit number by an 8-digit number, gives the 8-digit quotient and the possible rest. Duration of the whole procedure, 11 to 13 seconds. Of course, we laughed together about today about the speed, but I mean, it's a different thing. It's a pre-computer age still, right? We were kind of way electrified mechanical computers, right? And and then he says, everybody agrees that this is a respectable performance and begins to deplore that he once in his youth did the tiresome job of learning to calculate. I write hardly sound pedagogic advice because by Richard for me, this is because I think about our students today who don't learn arithmetic anymore, but take their pocket calculator. Then about functional analysis. As a part of rigorous applied mathematics, Trefethen says regularity theory starts from natural questions, but it has grown into a monster, consuming everything in sight. The question always, how smooth is this object? Here the numerical analysts have followed the theorists, and he complains about that. I'm speaking especially of the dominant technology for solving PDEs, known as the finite element method, which was also introduced by Courant and others. In the finite elements numerical analysis literature, you will rarely see a problem even stated, let alone investigated in any terms except Sobolev spaces, functional analysis. But what functions usually look like in practice is something else again. And so our mathematical analysis and our finite element algorithms in their standard forms fail to recognize or exploit the perfect smoothness, which he claims exists in reality for most of the applications. Right? That so many functions have almost everywhere in their domains. And then he has a kind of historical digression here, showing that this is the 18th century function here, analytic, then the 20th century, they were also Weierstrass already with these nowhere differentiable continuous functions. And then he says what functions really usually look like is piecewise analytic. So he wants us to come back to reality in a way, also in applied mathematics. So Ostrowski, Russian-born, Swiss-German Alexander Ostrowski, who was also a big shot in algebra actually, writes in his essay, which could still be translated, and it has never been translated to my knowledge, in German, tendencies that was represented with particular emphasis in the work of Lothar Kollatz. By the way, Kollatz is a student of von Mises. And his school, namely the strong use of functional analysis, which was also very much emphasized in the USSR, proved to be of resounding importance and became essential for the mentality of the numerical mathematicians of today. Functional analysis can only be practiced and applied in full rigor The concept of rigor has thus come an absolute postulate in numerical mathematics in our language area and can no longer be ignored by a fully trained numerical mathematician. He means the US came for, the USSR came for, and then in our language, in the German, they also accept it now. But I mean, look at the date. It's 1966. It's basically halfway into the computerization of mathematics. Yeah, basically no desk computers. And this is, by the way, some historical consideration by Prof on the history of numerical analysis, and he gives some predictions until 2050. So FFT is fast Fourier transforms and all these kind of known algorithms and methods, and also already software packages. He's starting with Chebyshev approximation under Garrett Birkhoff, Prof. So he says, I'm probably turned into the leading instance of mathematician who is applying approximation theory. So this gives me the opportunity to go a little bit into approximation theory, where this recommendable book is by Steffens here, which appeared just 2 years before Jefferson wrote in the Princeton Companion. Numerical analysis is built on a strong foundation, the mathematical subject of approximation theory. This field encompasses classical questions of interpolation, series expansions, and harmonic analysis associated with Newton, Fourier, Gauss, and so on. Chebyshev and Bernstein, Sergei Bernstein come into the theory, and sooner or later, everything boils down to approximation theory, he says. And then Ostrowski also says about Chebyshev, who is undervalued in a way, also in the historiography of science, I would think. Of course, not so much in probability, but approximation theory. So the cultivation of serious numerical analysis continued in Russia. There was less snobbishness, he says, there than in Western Europe, with unfortunately the gap between pure mathematics and its applications, especially to technical problems, was widened again and again in the 19th century. So we can look at this to connect to Runge. Runge published in 1901 über empirische Funktionen, Interpolation zwischen äquidistanten Koordinaten. So he has a rational function here, and he puts between equidistant points polynomials, and usually one would expect the higher the degree of the polynomial is, according to Newton's and other formulas, the closer would this polynomial express the original function, right? But it is not the case. We have the Runge phenomenon that if you use equidistant points, then we get, with higher degree, these kind of big aberrations. They go still through the given points, but then between the points, they're kind of oscillating the polynomials. And so they are not, the result is one should instead use not equidistant points, but more points at the sides at the margins of the interval, so that this gets closer there to the function which has to be approximated. By the way, he speaks about empirische function. It doesn't need to be a rational function at all, which is given. It can be just a table of values. So still can these methods be used, right? And then Trefessen refers to Hilbert's student Kirchberger, and this is an example for. I've never heard about this guy, and he was a Hilbert student, and in addition, what is a little bit embarrassment for me, he was Jewish and suffered under the Nazis, right? He was not an emigre. Embarrassment for me because I've worked on Jewish mathematicians, right? And he escaped me, but he was not an emigre for my book. So, and he's apparently important as a kind of step for the modern approximation theory. So it gives us new insights when these applied mathematicians look back on their history. So, and then he says, but here's what is crazy. How much better are optimal points? And their Chebyshev points are still not optimal. So this kind of division of the interval that denser at the end for approximation. Why is this good? 10% better? It turns out that they are 0% better. The trouble, to put it bluntly, is that approximation theorists are not very interested in approximating functions. They are interested in pursuing their mathematical ideals to the next logical step. So the whole literature of optimal interpolation points is pretty much an academic game. So I don't disregard the possibility that this is not common opinion by all numerical analysts, right? So yeah, he's going a little bit better. And this led to this funny name ChepFun later in a software package where this kind of Chebyshev approximation and more optimism was used. This is not yet in the predictions of the year 2000, which Jefferson published. So it shows how vibrant the thing is. So this is almost my last slide, which is good, so we have some time. So he speaks also of the rise of stochastics, both in pure mathematics and applied. Somehow, in more recent years, probability has moved to the center stage. You see this in the mathematics departments around the world. And starting in 2006, a regular fraction of Fields medals have been awarded for advances related to probability. Not to mention that Abel Prize to Varadan and another one recently to Fürstenberg. Recently, I marked a student paper that explained with the blitheness of youth that whereas in the past scientists modeled phenomena with differential equations, now it is recognized that these need to be replaced by stochastic differential equations. So then he says, I'm about 50% cynical about the rise of probability. It sometimes seems as if our computers have grown too powerful for the old problems to be challenging, so we make them harder by upgrading constants to random variables. So I leave this to the specialists of stochastics, whether this has any merit, this quote by Jefferson. So just because part of my task was to give you some literature, I give you some which is mostly related to numerical analysis. So for more literature on modeling, for instance, we had Tinner's talk, and so anyway, I could only kind of reproduce a very small part of numerical applied mathematics.
Thank you. For this extremely rich talk. Are there questions? David Aubin?
Thank you, Reinhard, for this talk. At some point, I don't remember who said that the distinction between pure math and applied mathematics was illusory, an illusion, and then they went on to say it was an attitude. This reminded me of Frédéric's talk, and I was wondering how far we can push that and think of the distinction between pure and applied mathematics as a fiction that's very useful to mathematicians, and it's a fiction that allows them to make choices. And you showed us you rely on some mathematician who clearly had made strong choices for most of your talk. And the question I wanted to ask is whether the choices Trefethen makes in 2022 to adopt the identity of an applied mathematician, is it the same choice that Runge made in the 1920s? Do you see strong differences between the choices that both mathematicians made to identify so clearly and so strongly as applied mathematicians.
Yeah, I mean, as the fiction is, of course, in this case, more of a kind of sociological fiction than the mathematical fiction. Courant was originally the guy who said that this is actually a matter of attitude, and then Trefethen explains that some pure mathematicians like this in a way because it's convenient for them to say, well, I could easily say things. Basically, we are doing also applied mathematics in store, and it doesn't need a special effort from us. So it's very ambiguous, also, this quote, you know. But it's very much recognized today that many historians, also Davis and Hirsch, and so speaking about the social dimension of dividing between pure and applied mathematics, and Trefethen doesn't like this attitude by the pure mathematicians who are kind of saying, well, then everything is solved for us, but if you could easily switch to the application too. So I mean, but there are parallels, and I was surprised actually in this book how strong the parallels are also to the Runge time, or to the when Mises criticized Courant at the time for forgetting about this. It has to be material. I mean, it's also about investments, you know, about computers and everything. It's also a material thing to that one is not satisfied by just this attitude thing. Yeah.
Michael?
Great, thank you, Reinhard. Lovely presentation. My question sort of starts in the same place as David's, but goes in a slightly different direction. So you've given us a large view of the forest of applied mathematicians based on the views of a small number of quite tall trees. And my question is, given that a lot of the views that you quoted are, obviously very opinionated, often mutually disagreeing, sometimes clearly facetious, especially when you're thinking like the Poincaré quote about convergence theories, he's clearly, exaggerating for effect. How reliable is that kind of testimony for characterizing the forest of applied mathematics, especially given what we know about the contextual diversity of applied mathematics in contradistinction to pure mathematics or to mathematics writ large in the periods that we're interested in?
Well, I'm afraid I cannot claim this is absolutely kind of representative. If I base many of these quotes on two books by two people, the one clearly not identical with the other because he's more responsible for modeling, and the other one more for numerical analysis. So computer specialists or people from computer science, which is now also sociologically, as Trefethen says, a little bit divided from the math departments in recent years, would maybe come to a different opinion without we can claim that one or the other is more in the right, or that is a better or more representative applied mathematician than the other. So we have to take all this with a cum salis, and to look at literature which is available here, and to make clear that it really needs, in certain cases, to reconsider existing historical reports and to uncover traditions which so far have been hidden for ideological reasons, maybe by Bourbaki or others which were not so interested. So I do not claim it. So it was my apology again. So.
I can testify to the fact that last July, when I attended the council meeting of the European Mathematical Society, there was an upheaval of people who considered themselves as applied mathematicians and who considered themselves as not sufficiently represented in the society, which shows that there are regularly tensions in institutions, and that the existence of chairs that are devoted to the existence of specific societies, the way in which in societies like the EMS the tensions are managed and so on, appears to me as an interesting venue in this issue. I'm sorry you raised your hand at the moment when we reached zero. I'm really sorry. I invite you to ask the question directly, and thanks a lot.